So for this problem, we want to find the particular solution for y equals x times dy by dx when y is equal to 2, when x is equal to 1. So unlike the last problems where we've been looking at finding the general solution, so we've had some kind of constants in there, for these problems, because we are given particular values, in this case for x and y, we want to be able to find out what those constants are. So, as with all differential equations, the first thing we need to do is separate our variables to get x on one side, y on the other. And because our dx is in the denominator here, we need to move that and the x term. So we end up with 1 over x dx is equal to, moving the y, 1 over y dy. As with all differential equations, after you've separated the variable, we then need to integrate both sides. So the integral of 1 over x with respect to x is ln x, and the integral of 1 over y with respect to y is ln y, and we need our constant of integration, which takes account of both constants. Now, normally, if we were looking for a general solution, we'd convert that into ln k, and you could still do that, but actually we don't need to, because we're given values for x and y, so we can substitute those directly to get a value for our constant. So when x is equal to 1 and y is equal to 2, you've got ln1 is equal to ln2 plus c. Well, the natural logarithm of 1 is just 0, so c is equal to minus ln2, or you can write that as ln a half. The minus becomes a power, 2 to the power of minus 1 is 1 over 2. Either is fine, and then we can just put this in here. So therefore, ln x is equal to ln y plus ln a half. If we rearrange this slightly, we can say that ln y is equal to ln x minus ln a half. Because it is a minus here, we can combine these two logarithms. The minus means that we have ln y is equal to ln x divided by a half, and if you divide by a half, that's times 2. So we can write that as ln 2x, taking the exponentials of both sides, and you're just left with y equals 2x, which is very nice because that is just a straight line. So from this differential equation, at this particular two values here, we generate an equation of a straight line that passes through the origin.